Hi everyone, welcome to our very first notes of the school year. Since this is our first one, I'm going to talk about how it works a little bit. Basically, these are the same notes that I would do if we were in the classroom, but we're not in the classroom, so I'm going to do them on video and upload them to YouTube. The one difference is I'm going to go a lot faster on these than I normally would in class, because in class I like to wait for you guys to, give you a chance to write things down or ask questions, where in this case, if you need to slow it down, you can just pause it, or you can rewind it if you want to watch something again. And if you have questions, you'll just have to email me. All right, so let's get started with 1.1, or which means Chapter 1, Section 1, and it's on functions. Now, because this is our very first section of the book, it's actually going to end up being one of our longer days of notes, because it's a whole bunch of little mini topics, things you guys have learned in the past that I want to review with you guys, and each one will take a few minutes. All right, so let's go ahead and start. All right, our first goal for today is to understand the word function, to get a definition for the word function. And before we can do that, we need to know what a relation is. And the word relation, it comes from the word relationship. If you have two different things, I'll call them X and Y, although it can be anything, two different variables, anything that describes the relationship between them, we call a relation. Now, a relation can have inputs and outputs. So usually if you're talking about X and Y, X is the input because you plug in numbers for X, and Y is the output because that's the answer that you get after you plug those numbers in. And remember, the letters can change. In a word problem, it probably won't be X and Y. It might be something totally different. So here's the definition of the word function, which is a very important word in math. If you have any type of relation or relationship between two variables, if every input has exactly one output, then that's a function. And let's talk a little bit more about that, because that is an important concept. So our first goal for today is to take a relation and decide whether or not it's a function. Now, the most simple type of relation is just an XY table. So for example, here are two different XY tables. Those are both relations. I mean, it describes the relationship. The first one says when X is 1, Y is 3. When X is 2, Y is 4, etc., etc. Now, I highlighted two little things with red lines there. That's to make those stand out to you. Because if you're talking about whether or not these are functions, one of those things is a problem, and one of those things isn't. So the reason I kind of highlighted those is in the first table, you're getting a 4 for an answer here, and also a 4 for an answer here. But they each came from different numbers. One of them we plugged in 2, and one of them we plugged in 4. Now over here, you have a 3 here and a 3 here in the X column. Now the second one is the one that's a problem. The first one doesn't matter. You can have all 4s in that Y column, and it can still be a function. But on the second XY table, one time I plugged in 3, and my answer was 4. Another time I plugged in 3, my answer was 0. That is not okay. That's not okay for a function. So again, that's a very simple example. The XY table is the easiest relation to look at, and we decided whether or not it's a function. All right, so the trickier one is if you don't have the XY table. Let's say you're just looking at an equation and trying to decide if it's a function or not. So for my example, I said, let's look at y equals x squared plus 1. And we start thinking, is there any possibility that if I plug in a number for x, I'm going to get two different answers for y? And the answer to this question is actually no. So I'm going to say this thing is a function. Any x I plug in, I'm always going to get the same answer. If I plug in 0 for x, y equals 1. That's never going to change. Every time I plug in 0, I get 1. If I plug in 5 for x, 5 squared is 25, plus 1 is 26, so I get 26. Never changes. So what I said on here is most equations, especially if they're in y equals form, are already functions. So what I want you guys to do right now, pause the video for a minute, Think back to all the different types of things you've learned in your math classes in the past and see if you can come up with one that is not a function, an equation of something you've done before that is not a function. Okay, hopefully you guys did that. You paused for a second and thought about it, came up with your answer. This one here is my answer. So my answer is a circle. A circle is something you guys learned about back in Math 4. It is x squared plus y squared equals r squared. So I just used 1 for r squared to make it simple. And I said that is not a function. A circle is not a function because if I plug in one number for x, if I plug in one number for x, I can actually get two different numbers for y. Now, the way you would see that, you can't see it by looking at it, x squared plus y squared equals 1. The way you would see that is by solving it for y. So let's put this into y equals form. Let me first subtract x squared from each side to cancel that out. And I get y squared equals 1 minus x squared. And then to finish solving for y, I take a square root of both sides. Now here's the real important thing, and I want you guys to just burn this into your memory and remember it forever. Every time you take the square root of both sides of an equation, you get two answers. You get a plus or minus. So what I get is y equals plus or minus square root of 1 minus x squared. And that plus or minus is actually the reason it's not a function. It's not a function because if I plug in a number for x, I'm getting two answers, one for the plus and one for the minus. So say, for example, we plug in 0 for x into our equation here. So I plug in 0, I get the square root of 1, which is 1, but I'm actually getting plus or minus 1. So I plug in 0 for x, one value, and I get both positive 1 and negative 1. I'm getting two outputs for one input, and that's what it means to not be a function. Okay, so to summarize, if you ever need to test whether or not an equation is a function, you first want to put it into y equals form. If it's already in y equals form, it probably already is a function. But once you get to y equals form, if you can think of any reason, like that plus or minus we just saw, where you're going to plug in a number and you're going to get two or more answers, then it's not a function. Okay, we're going to keep moving. Our second little mini topic for today is function notation. And in function notation, we already said x is usually the input. In function notation, instead of y, we call it f of x. Or we might call it g of x or h of x. You can name it whatever you want, but the idea is you name your function with a letter, usually like f, g, or h, and then you put the input variable, your x, in parentheses after it. We would say in words, f is a function of x, or we usually just shorten it to f of x. And what it means is plug in numbers. You know, if I say find f of 2, it means plug in 2. Now, there is one important difference between y and f of x. A lot of people think it's the same thing. You know, I have y equals x and I have f of x equals x. Those are the same thing. The only difference is that when I use function notation, I am telling you that it's a function. So if I call something f of x or g of x, you know it's a function, you don't even have to worry about it. If I say y equals, like I did on the last slide, then you don't know if it's a function or not. So that's the only difference. It's a way of the author, whoever is writing, or whoever is doing the math, that's a way of them telling you that it is a function. Okay, so let's go back to this concept here about plugging numbers in. And let's start with a really easy example. So we have a function f of x equals x squared plus 2x plus 4, and we're going to find f of 3. Now here's the thing. Even though this is an easy example, I'm sure that all of you could do it very simply. I'm going to go through it a little bit more slowly than I might otherwise because it's going to lead into a harder example. So when I give you f of x here, and I change that f of x into something else, in this case it's a 3, what I'm telling you is just take whatever you see there and put it in for every x in the question. Or the short way of thinking that is I'm substituting 3 for x. That's easy. So basically it goes like this. From the x from the f of x, whatever it turns into in the problem, you substitute that for each x. So what we end up with, if I do that, we end up with 3 squared plus 2 times 3 plus 4, which would be 9 plus 6 plus 4, or 19. So our answer is 19. Now I told you guys, that was an easy one. I'm sure every single one of you could have done that easily. The reason I went through it so carefully, so slowly, is because for the next example, I'm going to give you the exact same function, x squared plus 2x plus 4, and we're going to find f of x plus 2. Now that's a little harder question. That's one I've seen students miss before. But we're going to do the exact same thing. I'm going to take the x, and I'm going to change it into an x plus 2. Now what that means is I'm going to change each of these x's into an x plus 2. So what I'm going to have for my answer, I'm going to have, instead of x squared, I'm going to have x plus 2 squared. And instead of plus 2 times x, I'm going to have plus 2 times x plus 2. And then I still have that plus 4 on the end. So then you just finish it out. Now for the first part, oops, that part's not right. That's from my last slide. Let me back up here and I'll let me just finish it out by pen here. So the x plus 2 squared ends up being x squared plus 4x plus 4. And that's from foiling a binomial. Remember, you don't forget that middle term. Sometimes people just square the x and square the 2 and they think it's x squared plus 4. It's actually x plus 2 times x plus 2 and you get that middle term. And then on the second one, if I distribute the 2, I get 2x plus 4. And then I still have that extra plus 4 on the end. So if you combine your like terms here, you have the x squared, that's going to be the first part of my answer. We have a 4x and a 2x, so I get plus 6x. And then we have a 4, and a 4, that would give me plus 12. So there's my final answer there, x squared plus 6x plus 12. So that's 2 examples of how to use function notation. The first one was very simple, just plugging in a number. The second one was a little trickier, but notice like when I went through each one slowly, you're doing the exact same thing. If you look at what's on the top of the slide right now, you're just taking whatever is in the parentheses, substituting it for every x from the original function. Okay, our last little mini topic for today, and remember I told you this is one of our longer days of notes because there were several things I wanted to go over with you guys. Last little mini topic is domain. And domain is every number that x can be. And remember, x is your input. So basically any number where I plug in x and I actually get an answer, then that number x is part of the domain. So whenever you're doing domain, you can't go through and try to think of every number that works. You can't go, does 0 work? Yes. Does 1 work? Yes. Does 2 work? Yes. Does 0.379 work? I mean, numbers are infinite. It doesn't work that way. So instead, we flip the question, and we go, all right, well, what doesn't work? Most of them are going to work. What doesn't? So I said discuss. I'm going to have you guys pause the video for a minute again. Pause right now and just think about what might cause a function to be undefined. If I plug in x and the answer is undefined or does not exist or something like that, then that number is probably not part of the domain. So pause for a second and think about what can cause that. All right, hopefully you guys did that. You paused and thought about it for a second. Here is what we have so far. Any negative number under an even root. So if you have like the square root of a negative, that's undefined. So that would not be in the domain. Or a 4th root, or a 6th root, or an 8th root. That's why I said even roots. You guys remember when you learned about radicals in Math 5, odd roots are fine. I can take the cube root of a negative number. That's fine. I can take the 5th root or the 7th root of a negative. So if you have an odd root, don't worry about it. It's fine. But if you have an even root of a negative, that would be a domain error. 0 in the denominator is another big one. Anytime you get like 10 over 0 and you would say undefined for your answer, that's another example of a domain issue. Now, as of right now, that's basically all we have. As we move on through the year, I'm going to teach you guys some more functions. Logarithms have domain issues. Some of the trig functions have domain issues. So we are going to learn some more. But for right now, if I ask you guys to find domain of a function, all I'm asking you to do is check those two things. Are there any numbers that will give me a 0 in the denominator? And are there any numbers that will give me a negative in a square root or an even root? If you can find those values of x, those are not in your domain, and the domain is everything else. One last little note here. Every polynomial function is automatically all reals. Polynomials don't have denominators in them, and they don't have square roots in them by definition of the word polynomial. So if you have something that has no denominator and no square roots anywhere, don't even think about it. You just automatically say the domain is all real numbers. All real numbers means every x works. There are no problems. Domain is everything. So I'm going to wrap today up with two examples. One example that kind of shows each thing that we talked about. So first of all, let's find the domain of this function here. F of x equals 3x minus 1 over x minus 5. Now, we're only looking for two things. We're looking for a square root, which does not exist in this problem. If there's no square root, don't even worry about it. I do not have to worry about that because it's not here. I don't have to worry about getting a square root in a negative. I'm sorry, I don't have to worry about getting a negative in a square root if there's no square root in the first place. So forget about that. What I do have is a denominator. So I need to make sure that this thing does not equal 0. I don't care about the top. Leave the top alone for a domain question. 3x minus 1 can be anything, that's fine. I don't care what happens on top. Bottom moment. If that denominator equals 0, then it doesn't work. I don't get an answer. That means whatever x I plugged in to get it is not part of the domain. Now, a lot of people, this is an easy one. I think a lot of people are looking at it and automatically going, okay, x can't be 5. If I plug in 5 for x, I get 0 in the denominator. And that's the right answer. But if they get harder, just remember, mathematically, you can do it this way. Just take whatever is in the denominator, x minus 5, say it cannot equal 0, just like I wrote in the problem itself. Now, you can solve that just like any other equation. So I would solve this equation by adding 5 to each side. You can solve a does not equal equation just like in regular equation. So what that tells me is x cannot equal 5, which, like I said, we kind of saw that one anyways, is an easy one. But the answer to the question, that's the only number that x cannot be. So the answer to the question, the domain, is actually all real numbers except 5. That's what you would say. So basically, you're saying the domain is everything except 5. If I put in 5, it doesn't work. If I put in any other number, it does. And I kind of wrote over where that's going to pop up, so this might be kind of hard for you to see. But basically, it says there at the bottom, so the domain is all real numbers except 5. That would be the answer to that question. And let's do one last one. This will wrap it up for today. Let's find the domain of f of x equals square root of 3x minus 5. And remember, I said, you guys, for domain, we're only looking for two things. This is the opposite of the last question. The last question had a denominator, but it didn't have a square root. Now, this one doesn't have a denominator, so don't worry about that part. But this one has a square root. So I need to make sure that what is inside of it is never negative. So I'm not worried about the whole problem itself. I'm worried about the 3x minus 5. I need to make sure that that thing is not negative. So I'm going to take my 3x minus 5. Now, don't do not equal to. That's for the denominator. The denominator can't be 0. This one can't be negative. Now, if something is not negative, then it's either positive or possibly 0. 0 is okay there. You can take the square root of 0. The square root of 0 is 0, that's fine. It just can't be a negative number. So mathematically speaking, the way that you say you want something to not be negative is you want it to be greater than or equal to 0. Greater than 0 is a positive number, that's okay. Equal to 0 is 0, we said that's okay, but less than 0 means negative, and that's not okay. So as long as 3x minus 5 is either greater than or equal to 0, this one's going to work. If 3x minus 5 is less than 0, it's not going to work. Now just solve it like we did the other one. Add 5 to both sides. You get 3x is greater than or equal to 5. Divide by 3. And we get x is greater than or equal to 5/3. And that's your domain. Basically, if x is 5/3 or any number bigger than it, this function works. We get an answer. If x is anything less than 5/3, if it's 1 or 0 or any negative number, this thing's not going to work. And that's your domain there. It's all real numbers that are greater than or equal to 5/3. All right, that's the end of the notes for today. Hope that helped. Remember, if you have any questions, send me an email, and you can do assignment 1, which is on Schoology now.